Hello, everyone. First of all, I would like to thank the organizers for such a great organization, and mentors and mentees. Without them, we cannot do such a thing. My mentee is Dilan Demirtaş. She's a senior in Boğaziçi University Physics Department, and she's doing double major in mathematics as well. We studied knot theory, and from knot theory to knot invariants. Actually, our aim was to go to gauge theory, but it required too much information. So we changed our path to three manifolds. So today she's going to talk about from knots to three manifolds. Stage is yours.
Benim şu an sesim geliyor ama yakmadan. Tamam. The menu. Okay. Let's begin. I will be talking about the intersection between knot theory and three manifolds. So let us begin with a quick overview. I will start with an introduction why we study knot theory and what is our motivation behind it. Then I will give a definition of knot invariants and show an example of a knot invariant that we are going to use. Then we are going to construct Cyphered surfaces associated with a knot. Then we will calculate the knot genus from that surface and show that it too is actually a knot invariant. Then I will define torus knots, and I will show a process called Dehn surgery that we can use to create manifolds from knots. So let's begin with our introduction. The main problems of knot theory can be summarized in 2 points. Assume that we have 2 knot diagrams and we want to find out whether they represent the same knot or not. And on the other hand, we have to decide if a knot diagram is equivalent to the trivial knot, that is the knot with no crossings. And I will call that knot as the unknot from now on. And the original motivation of knot theory was to create an exhaustive tabulation of knots and links. From the beginnings of knot theory in the 19th century, there were more than 6 billion of knots and links tabulated. And in my talk, my aim is to build a connection between knots and three manifolds. That way, we can get a connection of knot invariants that we can use in classifying surfaces. So let's begin with the definition. I will define a more general concept called a link. A link L of M components is a subset of R3 that consists of M disjoint piecewise linear simple closed curves. And in particular, a knot is a link of one component. More intuitively, you can think of any closed loop of string in R3 as a knot. So here we have 4 equivalent diagrams of the trefoil knot. And we define a regular diagram as the diagram of a knot with the least number of crossing points. You see, pardon. This one has 4 crossing points, and this one too. But here we have the regular diagram of the trefoil knot with 3 crossings. And from now on, we will only talk about regular diagrams of a knot. Here we can see a knot table up to 7 crossings, and it excludes mirror images. We have our trefoil, unknot, and the figure 8 knot. And you see there are actually many knots that correspond to the same number of crossing points. And I talked about 2 knots being equivalent, but what does it actually mean? Well, 2 knots K and K prime are equivalent if we can obtain the knot diagram of one from the other by a series of finite Reidemeister moves. This is actually a theorem of Reidemeister, but we are not going to prove it. This corresponds to wiggling around, stretching, tangling, and untangling knots until it coincides with the other. We note that cutting and rejoining does not preserve equivalence. For if that were the case, we could cut and rejoin all of these knots to get the unknots. So here's a more pictorial description of Reidemeister move. The zeroth Reidemeister move corresponds to a polygonal description of the knot. We can deform it so as long as we do not change any crossing points. R1 corresponds to untangling a knot. R2 and R3 are pretty self-evident. You can see we have 2 overcrossings, so we can slide this thread towards the other. So we will find knot invariants now. We show that two knots are equivalent if they are connected to each other via Reidemeister remove. So we expect two knots to give the same knot invariance if they are connected with the Reidemeister remove. In that case, we expect our knot invariant to be unchanged under Reidemeister removes. For our purposes, we will use the linking number. To define the linking number, I will define the signature of a crossing. So let's say we have an oriented regular diagram and we have a crossing point C. There are two possible configurations. For each, we assign the following sign values. But to not memorize it and use a rather cool trick, you can use the right-hand rule. So your palm is going to face towards you at all times. Let your thumb point towards the overcrossing and your forefingers are in the direction of the undercrossing. If that's the case, we assign a positive value, and that's not the case, we assign a negative value. And let's find the linking number. So we have an oriented regular diagram of a two-component link, let's say K1 and K2, so that the crossing points of D at which K1 and K2 intersect are C1 to Cm. Then the linking number is half of the sum of the sign values of these crossings. It's called the linking number of K1 and K2, denoted by LK, K1, K2. Note that we do not care about the intersection points of K1 with itself, only the intersections of K1 and K2. So to prove that this is indeed a knot invariant, we should show that it is unchanged under the Reidemeister remove, but it's an easy task, so we will not delve into it. We will instead define a surface called the Cyphered surface from a knot diagram. We have a theorem. It states that given an arbitrarily oriented knot or link K, there exists in R3 an orientable connected surface F such that its boundary is the given knot. So to give a proof of it, we will use a construction and take a regular diagram D of the knot K. We want to decompose D into a series of simple closed curves. To do that, we splice the knot K along its orientation. So at every crossing point of D, we draw a circle like this and denote the intersection points with the circle and the knot by A, B, C, and D. And we delete the interior of this circle, then connect B to C and A to D. That way, we eliminate all the crossings of that diagram. As a result, D becomes a regular diagram of a link with n components without any crossing points. And we span each of these simple closed curves with a disk. To construct a surface, we now have independent and many disks. We need to attach them to each other via half-twisted bands. And the result will be an orientable surface that has the knot K as its boundary. And you can see a more clear account of the Seifert's algorithm. We have an oriented knot here, the figure 8 knot. We have our crossing, we eliminate that crossing and get circles. Inside the circles, we attach disks, and then we attach bands between these disks. There is a case for the trefoil knot. We have our knots, we eliminate our crossings, attach disks into our curves, and attach half bands so that we get the following Cyphered surface for the trefoil. So now that we have a surface from a knot, we want to calculate the knot genus, that is the genus of that Cyphered surface. And from the topological classification of surfaces, we know that a closed and orientable surface F is homeomorphic to a sphere with several handles attached to it. We call the number of handles as the genus of F. So we have a sphere that has genus 0 and a torus with genus 1 and so on. We want to obtain a knot invariant by defining a genus, but there are many Cyphered surfaces for a knot, so how can we define one? Well, it's quite easy. The genus of a knot is the minimal genus G of the Cyphered surface for K, and it is in fact a knot invariant. To prove this, we take two equivalent knots, K and K prime, with diagrams D and D prime and Cyphered surfaces as an S prime, and we let H be the homeomorphism that connects these diagrams. And we see that the Cyphered surface under this homeomorphism is a connected orientable surface with boundary K prime. So it is actually a Cyphered surface for K prime. That way, we see that the genus of K is greater than or equal to the genus of K prime. Well, on the other hand, a homeomorphism has, by definition, a continuous inverse. So the inverse image of S prime is a Cyphered surface for K as well. Then the genus of K prime is greater than or equal to the genus of K. That way, we show that for equivalent knots, we have equal genuses. As an example, we consider the unknot. Unknot clearly bounds a disk. We deform the unknot. We deform the disk so that we have the half cap. and we kept it off like this to get a sphere which has genus 0. In fact, the unknot is the only knot with genus 0. And we will define torus knots now. We take a cylinder in R3 with the unit circle C1 as its base and the unit circle C2 as its top. To define the trivial torus, we connect them such that the central axis C becomes the unknot. So that way we have our trivial torus. And a knot or link that lies on the trivial torus is said to be a torus knot or link. We can actually express torus knot in a standard way. We use the cylinder in R3 with unit height and unit circle as its base in the XY plane. To the base, we assign R points, A0 to AR, as follows, quite inductively. And the Z components are always 0, because it's on the base. And to the top, we assign R points as well. The only difference is that they are now on the Z component with 1. So we get the following picture. We have R points on the base, R points on the top. And to connect these, we take the path alpha I from the on the cylinder so that it connects AI to BI. Then we keep C1 fixed, the base fixed, and give the top C2 a rotation by 2 pi q over R, like this. So we rotate them, and B1 is not in the original position right now. And we then identify the XY0 point on the base with the XY1 on the bottom, right? XY1 on the top. So if we have A0 here, and if that's the point corresponding to another top point, we identify them. This gives a single trivial torus with R segments into a knot or link on the surface. It's called the QR torus knot or link, and we denote it by KQR. And upon identifying, we get this picture, this one. And this is a more clear diagram of the knot we have obtained. So here we have R rays, and we give them 3 twists. So this corresponds to knot K34. Then we need to create manifolds from links now. Before delving into that discussion, I will define what a length space is, because I want to build an example from that. We take 2 integers that are co-prime, let's say they are P and Q, and let P be greater than or equal to 3. And we consider following action over Z over PZ on S3 with generator sigma. Sigma takes 2 points and rotates them in the following fashion. Then we identify each X on the sphere with sigma X, sigma squared X, up to sigma to P minus 1X. Now this action has no fixed point since we took P and Q co-prime. This rotation always produces new points on the sphere. The resulting Cauchy space will be a 3 manifold. And we call this space as a length space and denoted by LPQ. We have the following lemma. I will not prove this, but you can get an intuition from the way we defined it. And the length space with coefficients PQ is homeomorphic to length space with minus P minus Q. And upon adding NP, the integer multiples of P, we get the same length space as well. So using this, we can equivalently take P and Q to be non-negative. In 1996, Massey developed the following definition. It is the definition of homeomorphism type, and it is characterized by 3 pieces of information for a surface: its orientability, its number of boundary components, and its Euler characteristics. So length spaces as 3 manifolds were introduced by Tietze in the early 20th century. At that time, they were the first known examples of 3 manifolds that were not identified using their fundamental group and homology alone. And also in 1919, Alexander showed that L51 is not homeomorphic to L52. This is interesting because they have the same homology and isomorphic fundamental groups. Well, a relief could be that they do not have the same homotopy type. But this didn't last long because L71 and L72 have the same homotopy type, the same homology and isomorphic fundamental groups, yet they are not homeomorphic. So this could be a nice point to illustrate the importance of geometric topology as a companion to algebraic topology. Length spaces will appear in more context in a minute. So let's define what a Dehn surgery is. Well, I do not have much time, so I will give a quick overview of Dehn surgery. We take an oriented knot K in S3, and we define the tubular region of it. That is, we inflate the knot, and we get this tubular region VK. then K is a knot. So the tubular region is a solid torus. Therefore, the boundary of that solid torus is a torus T. So we define two characteristic simple curves that defines this torus completely, a meridian M and a longitude L of T. T is not always the knot, so the resulting torus is not supposed to be the trivial torus always. We need to extend our notions. So meridian can be naturally extended to T. Meridian is this disk, and the longitude is this curve. For the longitude, we set it as the intersection between the Cyphered surface of K and the torus. So actually not the torus, the boundary of the tubular region. If we make the tubular region sufficiently thin, then this intersection is a simple closed curve on T. So just as one would expect from the longitude. Moreover, it is independent from the choice of the Cyphered surface. Then we assign an orientation to the meridian and the knot K such that their linking number is 1. And the orientation of the longitude will be the same as the knot K. Then we define another 3 manifold. Remember, why are we doing this? We need to create a manifold from a knot K. So we take the complement of the interior of this tubular region from S3, and they have a common boundary in our torus. And we denote its boundary as T prime. And since they have the same boundary, we can think the meridian and longitude to be the line on T prime as well. So we call them the meridian and longitude of T prime as 2. And we take a trivial torus T0, normal simp yani, place a KQR torus on it. Then we let a homeomorphism H to be the homeomorphism from the trivial torus to be T prime. That sends the meridian and longitude of the trivial torus to M and L. And this homeomorphism also sends the torus knot on the trivial torus onto the boundary of the tubular region. So it gives a QR torus knot K prime on T prime. And again, we define an automorphism H prime that sends the meridian of the initial torus to a torus knot K prime on T prime on the complement space. Using H prime, we glue the tubular region into the complement space along their boundaries T and T prime. So the resulting object is a closed orientable 3 manifold that has knot K as its boundary, and it's said to be constructed from S3 via Dehn surgery. Let's give a brief.
Can, I guess you muted. We cannot hear.
Okay. Tamam, şu an yeşil. Okay, şu an duyuluyorum diye düşünüyorum. As an example, the following manifold is actually the length space LQR. So we get, we have our trivial knot, and if we remove the
Bunun pili bitti mesela ya da bir şey. Bakın hocam yani. Yok o normalde açılıyordu. Bağlantı
Yok,
için.
şeye giriş yani. Tamam. Olabilir. Değil mi? Oradan bu giriş daha var.
Evet.
Girişi o. Hocam
Nasıl?
bilgisayarı yaklaştırıp onunla konuşabilir. Çünkü bu bilgisayardan ses gidiyor. Bilgisayar hafif. Bilgisayarı alabilirsin.
İstersen
Evet,
de
eline al.
Aha,
zor olmaz
Bakarak
da.
şey yapmak istiyorum. Tamam, şu an sesim geliyor mu? Buradan konuşacağım artık. Evet, mikrofondan evet geliyor, tamam. Artık devam ediyorum kaldığım yerden. As an example, the following manifold is actually length space LQR. And I stated the big theorem, and Licorice and Wallace proved this theorem by different methods independently. Licorice's proof is based on the following theorem. It says that any orientable automorphism of a closed orientable surface is generated by Dehn twists along 3G-1 simple closed curves, and they're specific in the surface, where G is the genus of the surface. If you do not know what a Dehn twist is, I have a picture here. It shows the effect of a positive Dehn twist along the red axis, and we see its effect on the green ray, as shown here. On the other hand, Walls gave a more general proof that involves adding handles to a boundary of a higher dimensional ball. Now, it follows that we have every closed orientable connected three manifold, and it corresponds to some link with an integer coefficient. So we can obtain every three manifold that has these properties by applying dense surgery along some link. But it may be the case that two inequivalent links may represent the same three manifold, given the right surgery coefficients. In fact, any knot with the coefficient infinity gives S3 back. Therefore, a classification of links does not induce a classification of three manifolds that trivially. However, in 1976, Kirby proved that if we have two manifolds, M and N, surged from links L and J respectively, then they're homeomorphic if and only if L and J are related by a sequence of alterations called Kirby moves. And contrary to popular belief, Kirby moves are not these ones. Evet, bu değil. Upon this, we see that an invariant of links with coefficients assigned becomes an invariant of three manifolds. And that's it. Thanks. Şimdi